So you have received up-to-date videos that have been captured, right? I'm not sure if any of you looked over the last one over the long weekend, but we are up to date. And I hope those help. You like those? Are they useful? Okay. All right. So let's see where we are. Any questions? Anything? Any problems? Any concerns? Any ideas? No? Okay. So let's move on. Where were we? We started the concept of rigid body equilibrium, which in a sense you can call that a preliminary or sort of a elementary type of structural analysis. That's what it is, sort of an introduction. This is your first exposure. So what was the objective, or what were the objectives of rigid body equilibrium, or equilibrium of rigid bodies, or rigid body analysis? There were two objectives. Number one was what? You remember, does anybody remember, what did we do? No, I mean, what the objectives were in rigid body equilibrium was first, find external reaction forces or support forces, right? Any structure you look at is supported somehow, right? And it is carrying some load. So as a first step, if you look at any objects in the world, our goal is to find all the forces that this structure is subjected to. These forces include applied loads, which are known, and those forces that come from the supports. We learn how to do that by cutting the supports away, replace them with equivalent unknown forces that, depending on the type of support, if you have a 2D structure, is a roller, a pin, or a fixed type support, you may have 1, 2, or 3 unknowns, right? And then we carried out the analysis by applying the equation of equilibrium to find those unknowns. So that was objective one. However, as I said, even back then, right, we also, in order to design a structure or a mechanism, we need to also find internal forces. What do we mean by that? A structure is not one continuous piece. It's made of components. An example that I've always referred to is the chair that you're sitting on. It's made of that seat, the legs, that platform you put your notebook on, and so on. So these pieces are connected together through bolts, maybe welded, or whatever, riveted. There are all kinds of mechanisms that hold these together. When you want to design a structure like that, you need to know how much each component basically is subjected to what kind of forces. The reason being that those connections, whether they're bolts or weld and whatnot, they carry some kind of a load, which is holding these two pieces together. We want to find out what those forces are, so that we can choose the right bolts, for instance. So the next objective then for rigid body equilibrium is to find those forces that hold pieces of the structure together. We call them connection forces or the joint forces. Okay? We're not going to, of course, obviously look at all kinds of structures in the world. And in fact, even we limit the coverage to mainly 2D structures when it comes to full analysis for internal forces. We will limit this coverage of rigid body equilibrium in this course mainly to two types of structures. Some schools in statics, they cover a third type of structure, which I wish we did too. In my previous lives, I always did that. But what we do here at Cal Poly, at least, is we study frames, and I would explain what those are, trusses, and we do not study beams, which is a different type of a structure or piece of the structure. We leave it for the next course, C204, stress analysis. Instead, we covered moment of inertia that we don't use in this course, right? We use this for that course, so don't ask me why. But anyway, so we will focus on these two. In order to make your life easier, it just dawned on me, it may not be a bad idea to give you a sort of an exposure or a glossary of what these two types of structures are all about, or how you can describe them as a first step. I've never done that. I thought of this, putting together this table very recently. So that's what I'm going to do. I will just first expose you to what basically defines these structures, or what are the attributes of each of these structures that define them as a frame or a truss. So, as I said, we cover two types of structures, frames and trusses. In fact, in the book, and almost in everybody does it that way, trusses are introduced first and then the frames. I do that the opposite, because I consider this as a general type of structure. Trusses are a special kind of that. So it's better to learn the more difficult topic first, or more comprehensive topic first, and then go to a special case, from the general to special, instead of from a special to general. So what are the attributes of these two structures that defines them being a frame or a truss? First of all, in terms of the loads that these structures carry, and the way they carry them. In frames, loads can be applied at any location on the structure. That means can be applied to the joints or along the member. You have no restriction. Okay? You're sitting on that chair. Load of your body is acting in that seat. You can move around and apply the loads anywhere you want on that seat. Not only that, that structure is designed such that there may be other possibilities. You may want to sit on, instead of sitting on that seat, stand on that platform. You know, it's crazy, but you know, it's possible. So loads can be applied anywhere along that structure. Okay? Connections of the members can be fixed, can be pins, or a roller. So there is no restriction how you connect them. You connect those pieces by welding them, or use a bolt to connect them. There are various types that you can do that. Okay. So this is how loads are acted on a frame. With trusses, of course, these are the assumptions we make for analyzing the structure. In trusses, loads are only applied, okay, at the joints. You do not allow, or you do not design trusses to carry loads along a member. Even if you have a, say, roof truss. You've seen roof trusses, right? A roof may be subjected to a distributed load, snow load. Not that you have snow in California, but other parts of the country. We make the assumption that, or when it comes to the design or analysis of these structures, that the loads are distributed such that part of the load, that distributed loads, goes to each joint. So the loads are assumed to be acting only at the joints. So that's as far as the attributes when it comes to the tolerance or the handling the external loads of the structure, okay? But then, how do members and connections are? In frames, okay, members can be connected to each other at any point along the member. That's number one. You don't have to, you have no restriction where to connect one member to another member, okay? Second, connections, whether they are internal, whether they are external or internal connections, connections that hold pieces together or connections that hold the structure together, can be also pins, fixed, etc. Trusses are not like that. Members are connected to each other only at their endpoints. You cannot connect a member to another member in the middle of the member. They can only be connected at the tip of the member, okay? Joints are only pins or rollers, right? So what does that mean? Does it sound familiar? Then in trusses, you can, if all the members are not subjected to any load along their length, the two end connections have to be pinned, right? And connections are only at the two ends. Two force members. You got three points already? Mm-hmm. No? Who got the 3 points? No? Nobody? So you get two then. Okay. So that means in trusses, are a peculiar type of structure. Every single member is a two-force member. In frames, you may have or may not have a member. If you have a member in a frame that is only connected at the two ends and the ends are pin connected and there's no load acting along that member is also a two-force member, but that's not necessarily the case. You may or may not have a two-force member in a frame, okay? All right, so with that said, how are we going to analyze or study a frame structure or a frame structure as the first type of rigid body structures for internal forces and find the forces at the connecting points? Any questions? Everything is clear so far? Okay, with that said, I cheated a little bit. I kept this drawing, in fact, to save some time and maybe can do more in this section than I did in the previous section, okay? All right, so let's see. So we will start with frames as the first step for rigid body equilibrium, okay? Okay, so frames. Again, remember the objectives. Objectives. 1, find reaction, supports. 2, internal forces. Okay. This is what I want to basically go over to set a sort of a methodical and organized way to do these problems. I don't expect you to memorize them, because after a while, you really learn or get the habit of using that approach to solve frame problems. Solving for the internal forces is not something that you just jump into it. You have to follow certain process, and basically builds on the main concept that the statics is all about. Free body diagram. You remember that 85% of statics? Okay. So I'm going to introduce basically a few steps. Step number 1, okay? What do you think is step number 1 is? Do you remember that from rigid body equilibrium, even finding external forces? Coordinate system. You establish a coordinate system because you want to know what directions your forces are with respect to that, and keep track of basically positive, negative values necessarily. Step number 2. Step number 2 and number 3 are really the heart of this analysis, okay? So you would do this. You take all pieces apart and draw the free body diagram for the entire structure as well as each member. I call that a member, any piece of the structure, okay? In doing so, you have to watch out for 2 things, okay? And I call that actually step number 3. Watch out for 2 force members. You remember what the 2 force member is, right? Just in case if you don't remember it, I will write it down. Connected only at the end points. End points are pins. Cannot be fixed, cannot be anything. It's pins. And third, no load acts along the member. Only at the end. Okay? That was a 2 force member. Which, if a member had those properties, then the load that carries is along a line connecting the 2 ends, a straight line that connects the 2 ends, regardless of the shape of that member. And these forces are equal in magnitude, opposite in direction. Okay? All right. So what is the step number 3? Or I call it step number 4 actually now. Okay? You draw, okay, you start with a free body diagram that has the least number of unknowns. Okay? Solve for as many unknowns as possible by applying equations of equilibrium. Okay? Exhaust all your options, all equations, meaning, and then move to the next free body diagram with the least number of unknowns. Okay? So those are the first four important steps, okay? So, step number 5, you continue basically continue step number 4 until you find all unknowns. And step number 6, okay, you would check and make sure you have used all free body diagrams except one. In other words, if you have done this correctly, you will always end up with one free body diagram that is not used. Okay? You only need n minus 1 free body diagram to solve for all your unknowns. Okay? And what is step number 7? Okay? Use the unused free body diagram to verify the results. And you are done. If that free body diagram checks out that all the answers are correct. If that, in other words, on that free body diagram you have all the forces because you found them from all the free body diagram that you have already used. So use that free body diagram, put all those forces you found, they should satisfy the equilibrium. If the summation of forces along X or Y or summation of moments do not turn to be 0, that means you've done something wrong. You have to go back and check. But as I said, there are two things you need to be careful, watch out for the two force members. There's something else that you also need to watch out for, but you know that already. I mean, so basically by now, you should know it by heart, and it's a trivial step for you, and that is, remember the law of action and reactions. As you're drawing these free body diagram, at each joint, if you make the assumption that unknown forces on one member are in certain direction, on the member that is connected to that, at that joint, would be the opposite directions, okay? So, is that clear? Any questions? Okay, if not, let's see, I save the time by making this problem and leaving it here so that we can save some time and start attacking a specific problem and get these steps applied and see what we do and how we proceed, okay? So this is a good example that I made it up because it has almost everything that I want, except that, connections are all pins, can be maybe one or two connections, don't have to be, but this is a very good problem. You have 5 clearly defined members in this structure. So what did I say? Where the steps were? Step number one, you set up an X and Y coordinate, right? That's the easy step. Step number two, you start taking all members apart. So that's what I'm gonna do. Okay? Start with this member, A, B, F. And it's a good idea to label these members as you taking them apart. So, before doing that actually, you don't have to start with that free body diagram. It may be actually a good habit that you start with the entire structure as the first free body diagram, especially that you know how to do it, right? It's quite a familiar thing to you. So this is the structure, right? So why not actually starting with that as the first free body diagram, right? So all you need to do, just take these supports away, right? And put back their effect. And you remember that these directions are arbitrary. So I'll take this out, you have a roller here, so the unknown here is perpendicular to the potential direction of motion. So if that is 60, this is 30. You have one unknown here, which is recommended if you resolve that into its components. So let me do that. If I call this R at H, right, that's what that was labeled. So this would be RH cosine of 60. This is RH sine 60, okay? So that's the free body diagram of the whole structure. Now I'm gonna take things apart. This is member one. At A, we already had made the assumption that the forces are acting like this. At point B, I don't know what directions those forces are. It's a pin, carries two forces. So let's make the assumption that Bx and By are like this. Be careful, remember the law of action and reaction. If you make that assumption for the direction of forces at B on this member, when you draw the other member that is connected to this member at B, corresponding forces would be the same but in the opposite direction. So let's first take care of this. And at F, who knows? I'm just assuming these forces are acting like this. So that's member number one, okay? Member number two, let's consider this to be member number two. So you have member B, C, D, it's a little bit longer than that. Okay, okay, this is D, and this is I and J, okay? So that's this member. At point D, you have forces that you need to watch out. Make sure you choose them in the opposite direction to that member. Because at that point, you have forces equal in magnitude, opposite in direction, right? At C, you have an externally applied load of 300 Newton. At D, again, I don't know what forces, in what directions they are, but this is a pin, so I would assume that you have two forces in this direction and this direction. It's the first time you encounter those forces, right? At J, you have a pin, that pulley is connected to the member through a pin. So this pin represents two forces, Jx and Jy. I forgot about I. How about at I? The pin connections. How many forces do you have there? How many forces? Anybody? Two, right? Everybody agrees? Wrong. One. I gave you a warning. Watch out for two force members. Do not underestimate that. If you do not detect two force members, your life will be miserable in analyzing frame structures. You may not be able to solve the problem for all the unknowns. So look at this joint. You have a member connected only at the two ends. Number one, these endpoints are pin connected. Number two, no load acts along this member. The third property or the attribute of a member. That means if you consider, look at that member. Let me call that member number 2. Let me call that member number 3, right? If there is any force at the end joints, it's only a single force. Okay, I call that, say, R and I, so this would be R and I. Same at the two ends, acts along a straight line connecting these two ends. It is a two-force member. Two-force member. Okay? So let's move on. Okay? I have member EDFG now. At E, I have just a cable attached, so we know this is only represents only one unknown. At I, right? I'm sorry, at D, I already had D somewhere else here. At this on this member, I assumed forces at D on this member act in this direction, so. On this member, you have to make the assumption that they act in the opposite direction. Same thing at F. You had already encountered F here on member 1. So if the force on member 1 acting in this direction, corresponding forces on this member, you need to make the assumption that they act in this direction. And how about at G? At G, you have what? You have only one force. If this is at G, acting from that member, so the force on G would be like this. Okay? And obviously, of course, here, which I did not put it, is also like this. And how about here? Here you have this RH cosine 60 and RH sine 60. Okay? So that is member number 4. Do we have any member left? Anything left? The pulley. Pulley is a member. And it is connected at point J to that member, right? And the assumption was that the forces were in this direction. First of all, there is a force of 100 Newton here, so it would be a force of 100 Newton here. And this is, of course, that same. So the forces at J would be in this direction, Jx, opposite to this, and I make the assumption that would be in this direction. I'm not saying that the assumption is right, but that's what I assumed. So this is member number 5. Any more members left? No, we're done. So that completes step number 2, and actually step number 3, which, as I said, would watch out for the two force members, which was 2. two-fourths members. So step number 4 now, right? What is step number 4? You begin with a free body diagram that has the least number of unknowns. So let's look. Number 1, how many unknowns we have here? 1, 2, 3, 4, 5, 6. Number 2, 1, 2, 3, 4, 5, 6, 7. Number 3, 1. Number 4, 1, 2, 3, 4, 5, 6. This was 1/4, right? Here, 2. So which free body diagram should I start with? You start with 3, but remember, anytime you have a 2/4 member, the free body diagram of that member you've already used. In fact, already applied the equations of equilibrium to figure out that these two forces are equal in magnitude and opposite in direction. So because of that, remember that diagram for the 2/4 member is useless. So that I have already used. Any free body diagram you've already exhausted all your options on, put a check mark next to it, right? Because here you have only what? Equation, sum of forces along x and y equal to 0, which gives you those to being equal. So what free body diagram is next then? 5. So I'm going to start, so I would put here 3 already used. I'm going to start with 5. And I use all equations of equilibrium. So I write summation of forces along x is equal to 0. I get jx minus 100 is equal to 0. So jx is 100 Newton. Okay? As soon as you find an unknown force, it is a good idea, put either something like this, a cross over it, or check mark, whatever. So you can, anywhere that force appears, throughout all these free body diagrams. So you found Jx there, so you know that you have also Jx here. So you can keep track of how many unknowns is left again on each free body diagram. So now I write summation of forces along y is equal to 0. You have negative jy, right? Okay. Negative 100 Newton is equal to 0. So jy is negative 100 Newton. What do I do? Those concepts we learned so far about rigid body equilibriums, they hold. You should remember those. Those are important. So what do I do here? I would immediately change the assumed direction, right? But not just here, on this diagram, everywhere that force appears. Change this, okay? So this should be like this, and put a check mark that I have done that, right? So free body diagram number 5 is done. So I'm now going to go back and look at again all the free body diagrams. How many unknowns here I have here? Still 6, but how many here? 1, 2, 3, 4, 5 here now instead of 7. And here, 1, 2, 3, 4, 5, 6. So what else? I have that guy over there sitting. Think of that guy too. How many unknowns I have there? 3. So which one do I start with? Or use as the next one? 6, 5, 6, or 3? 3, right? So I'm going to use that free body diagram, right? So I'm gonna come here. So, and what do? I will take summation of moments about A is equal to 0. All those good things we had learned, right? About applying equations of equilibrium still holds. Take summation of moments about 2 unknowns to get rid of them. So I have only 1 unknown left. So let's do that. I have 1 force here. The distance is what? This is 2. This is given as 2, right? This is 9. So 11 and 18 would be what? 29 and 6, 35. So you have a force counterclockwise of 100 Newton times 35 meters. That's the moment of that force. Then I have these two. This is counterclockwise, so it would be positive. So I have plus RH sine of 60, right? Which is square root of 3 over 2 times this distance, which is 25. I'm sorry, 24, 18 and 6. This guy is, again, clockwise, and it is negative then. So you have negative RH cosine of 60, which is 1/2 times this distance. This distance is 12, okay? So times 12 is equal to 0, okay? So I have RH times 12 square root 3 minus 6, okay, is equal to 3,500. So somebody's going to give me RH.
I think you forgot one.
I'm sorry? Oh, you know what? There was also this force. Good observation. Somehow I overlooked that guy. You also have 300. That is negative. So that is good. So negative 300 times this distance, which is 15, is equal to 0. So I have 4,500 and then 3,500. That is 8,000. So could somebody give me 8,000 divided by 12 square root of 3 minus 6? I need that. RH would be positive.
541.
How much?
541.
541 Newton. Okay. So you have 541. So now I use summation of forces along X is equal to 0. So I have AX, right, minus RH 541 cosine 60, which is 1/2, is equal to 0. So AX would be 270.5, right? That's Newton. Then you have summation of forces along Y is equal to 0. So you have RH sine, you have 541 square root 3 over 2, okay, minus 300 minus 100 plus AI is equal to 0. So that'll give me AY would be how much? 541 square root 3 over 2 minus 400. Could you give me that one? Anybody? You gotta do some work. Yes.
Yeah, 68.5.
68 what?
0.5.
68, oh, that's good. So 68.5 Newton, and that turns out to be positive. So that means I've used this free body diagram. You have this one now, AX, you have AY, right? And you also have this one. maybe I'll use a different color. So all those unknowns that you found on all free body diagram, make sure you take care of them. So I have this one, okay? Okay, so now let's look at how many unknowns we have left. Again, 1, 2, 3, 4, right? 1, 2, 3, 4. Here, 1, 2, 3, 5. So which one is logical to use? I have 4 here, and how many here?
4.
4 here. No, here I have 5, right? 3, 5. Here I have what? 4. And here I have 5, right? So which one do I use? I will use, obviously, this one, okay? Okay, so let's do that. Yes?
The AY is a negative 68.5 newtons.
AY is negative 68? Oh,
Yes.
so it came out to be the, so thanks for telling me that. So that means the assumed direction here was wrong. So this has to be corrected. And where else I had this? AY also has to be corrected. So if that is, okay, oops, no, I'm sorry, that is the same. Okay, so this one and this one, okay. All right, so I'm going to use, I'm afraid I have to erase something here. So I will use free body diagram number 1. So if I use free body diagram number 1, I will take summation of moments about point B is equal to 0. That way I get rid of these two, and this one, I only have one unknown. So if I take summation of moments about that one, AY, which is 68.5, makes a moment about point B. You have that distance 6 in the opposite direction, counterclockwise. FY makes also counterclockwise. You see, if you make summation of moments about here, these two don't make any moment, you have only these two. So an FY, its distance from there is, how much is 18? Is equal to 0. So this is 3, this is 1. So Fy comes out to be negative 2, almost 22.8. It came out to be negative. So the first thing you do is what? Change that. Here, and where else does it appear? Here. Okay? So correct that here. So that's Fy. You write summation of forces along y is equal to 0. So you have negative dy, negative 22.8, which is Fy, and negative ay, right? Which you had that, ay, you found ay was 68.5, right? So 68.5 is equal to 0. So by comes out to be negative, right? $91.3. That means again what? By, the assumption for its direction is wrong, so you have to change that. Here, okay, and where else does it work? Here. And you've done that, and this one here, okay? So you have Fy, and you have also By there, okay? So So you've already used summation of moments here, summation of forces along y. Now the one you have left is summation of forces along x, okay, is equal to 0, okay? So time is up, and we have a lot more to do, but you got the process. You just keep on continuing this until you're done. Of course, we're gonna finish this problem tomorrow, okay?